Let's do the following question. State Faraday's law. So Faraday's law states that the magnitude of the induced EMF, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. So it's given by E is equals to minus N d phi dt. So that is the formula that is derived from Faraday's law, where d phi dt represents the change in flux, and this is from Lenz's law. This is the negative is from Lenz's law, and N is the number of turns in the coil. So you have to label that N is from Lenz, N number of turns, and d phi dt is equals to rate of change of flask. Rate of change of flask. So let's move on to the following. Two coils X and Y are placed close to each other as shown in Fig 1.1. Describe and explain the observation on closing switch S. So as you can see here, when you close this switch, so let's put the diagram into perspective. When you close the switch S, there is a current that moves in this coil. So this current, when the current moves here, it creates a magnetic flux. It creates a magnetic flux. So since the current is moving from 0 to max, since it's moving from 0 to max, so d phi dt, so the time taken for the current to move from 0 to max, which means there's going to be an EMF induced here because the magnetic flux is increasing, so there's going to be a deflection in the opposite direction of the flow of current here. The galvanometer is going to show a deflection. So there's going to be a deflection here because the d phi dt, the flux is changing from 0 to mass, so there's going to be a deflection in the opposite direction. So let's do another question. When S is kept closed, so when S is kept closed, so there's going to be constant current moving here. If S is kept closed, constant current is going to flow here, so the flux is not changing, so d phi dt becomes 0. And if we look at our formula, if this becomes 0, there is no induced EMF. If this one is 0, the current is constant. So only a change in current will cause a change in the magnetic flux, and that's why we can record an EMF here. So when F is kept closed, there is no change in current, so there's no change in magnetic flux, so the galvanometer remains at 0. When S is opened, so when S is opened, d phi dt moves from maximum, it moves from max towards 0, so there is a deflection in this direction, which is opposite. So the movement from max to 0, which means d phi dt will be negative, so we are going to have an EMF induced because d phi dt is no longer 0. So explain how the observations verify Lenz's law. So on closing the switch X, the flux through Y increases induced current in Y flows in opposite direction. So you can see that Lenz's law says that this galvanometer, the induced current here, should flow in the opposite direction. Remember our equation, the negative comes from Lenz's law. We say that the induced current EMF here will be opposing the magnetic flux that is produced by this coil. So when you close here, the EMF was moving towards this one, but the galvanometer was in the opposite direction, which proves Lenz's law, which means the current that's going to be induced here is moving in the opposite direction as the current that is in here.